So far we've looked at the Bronsted-Lowry concept of acids and bases. So the Bronsted-Lowry concept considers acids as being something that can donate a proton, and bases being something that can accept a proton. So it applies to a wide range of reactions, but all of these reactions have to include a proton transfer to be applicable. So it's useful to have a more general acid-base concept, and so one was developed by Gilbert Lewis in the 1930s, which expands this idea of acid-base reactions to a wider range of reaction types. So in the Lewis definition, an acid is some substance that can accept a pair of electrons from another atom, so either within the same molecule or from another molecule, and in accepting a pair of electrons it forms a new bond. And a Lewis base is a substance that can donate a pair of electrons, so it donates this pair of electrons to another atom and again forms a new bond. So there are a variety of types of Lewis acids. So the simplest example would be just a proton, which we already have seen in the Bronsted-Lowry definition of acids and bases, but it turns out that a proton is also considered a Lewis acid. And so the Lewis concept of acids encompasses the Bronsted-Lowry concept of acids, but it also expands it. So in addition to protons being acids, we also see that metal cations are Lewis acids, specifically, or most commonly, metal ions of transition metals with fairly high positive charges, so charges of 2 or 3. And then we can also have molecules that have electron deficient atoms. These can also be Lewis acids. So trihaloboranes and trihaloaluminum, as well as carbon dioxide and sulfur dioxide, are all examples of molecules that have electron deficient atoms, and because of this, these atoms can accept a pair of electrons and react as a Lewis acid. Now, the Lewis concept of the base actually encompasses the same species that the Bronsted-Lowry concept of a base has. So, in the Bronsted-Lowry concept, a base has to be able to accept a proton, and so in order to accept a proton, it has to have a pair of electrons. And so this applies also to the Lewis definition, where in order to act as a base, the molecular anion has to be able to donate a pair of electrons. So again, it has to have a lone pair of electrons. And so the same things that we saw as Lewis as Bronsted bases are also Lewis bases. So species like hydroxide and chloride, as well as ammonia and water, can be considered Lewis bases. So in general, the reaction between a Lewis acid and base is always going to involve each of these species to form a new bond, which results in a new chemical species referred to as an adduct. So as I mentioned before, protons are also Lewis acids and Bronsted acids, and a proton reacts with water. This is a proton transfer reaction we've seen many times to form hydronium. So in this case, the proton is also acting as a Lewis acid, water is acting as a Lewis base, donating one of these lone pairs of electrons and forming what we call an adduct. Now, the proton can also react with other Lewis bases. So, for example, ammonia has a lone pair of electrons on a fairly electronegative atom, nitrogen, and so it can donate this pair of electrons to the proton to form the ammonium cation. Now, in addition to protons being Lewis acids, metal cations can also act as Lewis acids, and the reason for this is that they very often contain empty d orbitals that are of approximately the right energy to accept a pair of electrons and form a bond. So cobalt-2+, for example, in water will react to form an adduct with water. So in this case, the cobalt-2+ is our Lewis acid, and the water is our Lewis base. And we form a new coordinate covalent bond between the oxygen on the water and the cobalt-2+. And very often it's favorable for metal ions to form multiple coordinate covalent bonds with water or other Lewis bases. And so cobalt and many other transition metal ions, it's most favorable to form 6 of these metal-oxygen bonds, and so they form structures that have octahedral geometries, where each of the angles between the water molecules are 90 degrees. Now, certain metal ions it's more favorable for certain metal ions to form only a 4-coordinate complex, so they form these tetrahedral complexes, again, where 4 waters are bound to the central metal ion. In all of these cases, the metal-oxygen bonds that form are referred to as coordinate covalent bonds, and the adducts are very often referred to as complex ions. So in each of these cases, these metal-aqua complexes are actually also referred to as complex ions. So let's look at some examples of other Lewis acid base adducts that involve things other than water acting as the Lewis base. So on the left here I have the heme group in hemoglobin shown. And just this chemical species alone is an example of a Lewis acid base adduct. The iron 2+ is electron deficient, so it can act as a Lewis acid, and each of these nitrogen atoms on this ring, which is referred to as a porphyrin, are going to have at least one lone pair of electrons that they can donate to the iron 2 center. So just in forming this heme group, that's the active part of hemoglobin, is an acid-base adduct. Now, in addition, the iron 2 binds oxygen, which gives hemoglobin its activity, and this also is a Lewis acid base adduct. So again, the iron 2+ is acting as the Lewis acid, and the oxygen is acting as the Lewis base. And another example of a Lewis base that can bind to iron is carbon monoxide, and carbon monoxide is toxic to us because it's able to disturb the activity of hemoglobin, because the adduct that forms between iron and carbon monoxide is actually more stable than the adduct that forms between iron and oxygen. So once carbon monoxide binds, it can't be displaced by oxygen, and so you lose the activity of the hemoglobin. Another example of a Lewis acid base adduct is between copper and ammonia. So copper 2 tends to form 4 coordinate complex ions that have square planar geometry, so each of these angles is 90 degrees. And again, the ammonia, the lone pair of electrons on the nitrogen of ammonia forms a coordinate covalent bond with the copper 2 ion. Now, we've seen before that aqueous solutions of many transition metals that have 2+ or 3+ charges are often acidic, and this is because, as I've said before, they undergo hydrolysis. So now let's think about why this is actually occurring. So if we have aluminum 3+ in aqueous solution, we have an aluminum ion that could potentially form an adduct with water because the oxygen in water has a lone pair of electrons that it could donate. And it turns out that this interaction between aluminum and oxygen ends up weakening the OH bonds. And the reason for this is that some electron density from the oxygen is being taken away from this part of the molecule and donating to the aluminum 3+. So this in turn weakens the OH bond and increases the electron affinity of this oxygen atom, and so the water is now prone to deprotonation by another water molecule. So another water molecule in close proximity can remove a hydrogen atom as H+, and now that would lead to an acidic solution. So the reaction that's occurring here is aluminum forms a 6-coordinate complex ion with water. In the presence of other water, because these OH bonds are weakened by the interaction between aluminum and water, another water can act as an base and deprotonate the aluminum aqua complex. And so now we have 5 water molecules and 1 hydroxide ion bound to the central aluminum atom. And so now, because we have 1 anion in the complex ion, the overall charge decreases. And we now also have hydronium ions in solution, and so the solution ends up being acidic overall. And so anytime that you have a fairly highly charged metal ion, this kind of interaction can occur and leads to acidic solutions. Now, there are also examples of adducts that can behave as acids or bases. So an example of this is aluminum hydroxide. So in this figure, we have shown a solution that contains the aluminum aqua complex. So most likely this was prepared using a soluble aluminum salt, aluminum nitrate being one of the most common soluble salts. And so we have aluminum and nitrate ions in solution, and so because we're in aqueous solution, we actually have this complex aluminum aqua complex ion forming. Now, if we add ammonia to this solution, we're adding ammonia in water, And so we know that ammonia is a weak base, and so this leads to the formation of some ammonium and hydroxide. And the hydroxide reacts with the aluminum and forms aluminum hydroxide, which is an insoluble compound. So upon addition of ammonia, which is an indirect source of hydroxide, we end up forming an insoluble aluminum hydroxide. Now, if we left the aluminum hydroxide alone, it would stay as a solid in the aqueous solution. But if we add sodium hydroxide, as I have shown in this step, all of the aluminum hydroxide ends up dissolving. And so what is going on that leads to dissolution of the aluminum hydroxide upon addition of excess hydroxide? So what happens is that we actually form a new complex ion. And so with excess hydroxide present, the hydroxide bonds to the aluminum on the aluminum hydroxide, and this forms a 4-coordinate anion that actually is water-soluble. And so all of the aluminum hydroxide ends up being converted to this complex ion, and so it all eventually dissolves in base. Likewise, if we add HCl to the mixture of solid aluminum hydroxide and water, the solid will gradually all dissolve in the HCl. The reason for this is that we're adding an acid to this aluminum hydroxide, and so this hydroxide still has a free lone pair that it's not using to bond to the aluminum, and so we can protonate the hydroxides, and they can be lost as water, and then we're left with just aluminum-3 ions in solution, which we know will reform a aqua complex with water. But we've now basically consumed the hydroxide and formed more water, leading to dissolution of the aluminum hydroxide. And so an amphoteric metal hydroxide is something where in the first step, the aluminum is acting as a Lewis acid, so it's accepting a pair of electrons from this hydroxide. And then in the bottom reaction, the hydroxide on aluminum hydroxide is accepting a proton from hydronium, and so in the bottom reaction it's behaving as a Bronsted acid, or a Bronsted base. So an amphoteric hydroxide is going to be something that can behave as a Lewis acid and a Bronsted base. So as I mentioned before, in addition to acids being cations, we can also have molecular Lewis acids. So an example of this is carbon dioxide. So in carbon dioxide, the CO bond is quite polar, with the oxygen atoms having fairly high partial negative charges, which in turn leads to a high partial positive charge on the carbon atom, and this makes it prone to attack by a lone pair of electrons on hydroxide, and so we can form this new Lewis acid adduct that has a negative charge overall, where we've now formed an OH bond, a CO bond between the hydroxide and the carbon on the carbon dioxide. And then the last class of molecular Lewis acids is boron trichloride. And so in this case, the boron in the boron trichloride is electron deficient, and so it can accept a pair of electrons from ammonia, for example, and this is going to go on to form a borane ammonium complex. So we formed a new neutral species from two neutral species through this Lewis acid base reaction. So take a few minutes to try and determine whether each of these species would behave as a Lewis acid or a Lewis base. In each case, it's best to draw the Lewis structure and then determine if the central atom has lone pairs, which tells you that the central atom can behave as a Lewis base. If it doesn't have any lone pairs, that's an indication that it can behave as a Lewis acid.